How's it going, guys? We're going to be working on Leetcode medium today. Question number 1448, called Count Good Nodes in Binary Tree. So let's get started. In this question, we're given a tree, and we want to return the number of good nodes in the binary tree. So the definition of a good node in this question is defined here. Okay. Given any node, let's call that node X. If we want to figure out if X is a good node, we check if from the path of starting from the root all the way down to the node X, if any of those values are greater than node X, then that node is not good. In other words, if none of the nodes starting from the root to node X is greater than node X, then that node is considered to be a good node. So in this case, say in this tree we see that the blue nodes are considered to be good nodes, therefore we're returning 4. And as an example here, if we want to figure out if 5 is a good node, okay, so the node 5 is our node X, okay, and we start from the path starting from the root all the way to 5. So starting from the root we have 3, and then we have 4, and then we have 5. So we see that 3 and 4 is not greater than node X, which is 5. Therefore 5 is a good node. Same logic applies to 4. The path from the root to 4, no nodes are greater than 4. Well, other than itself, which is equal, but we don't count that. And then if we look at node 1, well, starting from the root, we go the path goes from 3, 4, 1. 3 and 4 are both greater than number 1. Therefore, this node with the value 1 is not good. That the same logic goes for 1. This one is a little bit. This node right here is a little bit interesting. So we want to figure out if this node 3 is considered to be good. So we start from the root and find its path down to node X. So we see that 3 is not greater than 3. Well, so right here it's fine so far. But then we hit 1, right? Well, 1 is still not greater than 3. So 3 and 1 is not greater than 3, which makes 3 actually to be a good node, even though 1 itself is not a good node because 3 is greater than 1. But this 3, this leaf node 3, if we start from the root, these two values are equal, and 3 is obviously not greater than 3. Therefore, it makes this leaf node 3 to be a good node. Okay, so as I said before, we're going to have a couple of things we want to keep track. We want to have a variable to keep track of number of good nodes, and we could do this in a number of ways. And then we also need variable to keep track of max, right? Because at every recursive call we want to be able to keep track of the max. Okay. So like many recursive calls, one way people usually do it, well, common way people do it is to have a nested function. Let's call it DFS, and then this is a wrapper, and it's gonna take in the root, and then we're gonna traverse this using DFS, and every single time that we call DFS, we're gonna be changing max so far, depending whether or not the current node value is greater than the last max. Okay, so let's just make the recursive call here. So we're gonna call TFS, we'll call root. What are we going to send in to be our max so far? Well, we want to be the lowest value as possible when we send it in, because we never actually want this random value to ever be the max. If we make sure that it's the lowest value possible, it never will be max. And we see that each node's value is negative 10 to the power of 4, so we could really just do negative 10 to the power of 4. Okay, or you can do int min, but I just chose to do this. Let's just say okay, actually int min is a better practice. Okay, sounds good. So we also want to have a non-local variable, so we can increment this in our nested function whenever the condition is satisfied. So non-local number of good. This is what we're going to be incrementing every single time we do find a good node. And what are we checking? So remember, we're checking if the max so far, right? This is this is our max so far. This is our max so far, right? These are our max so fars. And we're checking the current value. If the current value is greater, well, I messed up here, but it should be greater or equal to the value here, right? Because if it's equal, it's still fine, because we need to add a value. We need to find a value that's actually greater than the node value. So as long as as long as the node value, as long as the node value is greater than, or we could say that the current max is less than or equal to the node value, then we are fine. So we could say here that if the node value dot val is greater than the max so far, okay, so if this is ever true, actually we want to check if the max so far is less than or equal to no value, because then that's when we increment our number of good nodes. We add to 1. Otherwise, we to check if the leaves, to check if the right one is not at a dead end, so it is not none. So whenever it is a node, then all we do is go down to the right and we say node.val, and then we are going to say max of node.val, right? We're going to take the max of node.val, so max so far, okay, right? This is where the max comes in. We're taking the max of 4 and 3. We're taking the max of 5 and 4. Here we're taking the max of 4 and 3, max of 1 and 4. And during the first loop, invisible loop here, we're actually taking the max of 3 and we're taking max of 3 and int min. So once we have this, do the same thing for left. If left is still a node, then we say that node, we're gonna recursive call it going left, right? This is a DFS. Our max so far is going to be the max of, oops, messed up here, max so far, okay, save some space here, and then at the end we just say return number of good nodes. Okay, again, if the max so far is ever less than the current value we're on, it's a good node. If the right is not a leaf, then let's keep going to the right and make sure the max gets updated accordingly, which is between the current value and the last max so far. Do the same thing to the left, and then we're gonna start with a number of good nodes is 0. We're gonna call a wrapper function, send in the root, send in the int min as our max so far, and then again return number of good nodes. If we run this code, we have a weird indent Okay, let's run this again. Okay, so we got some weird indent. Let's fix that real quick here. So it's fixed now, and we submit. We do have the right answer and accepted. For the runtime of this question, we are going through each node only once, so it'll be O of n. And then as for the splice complexity, the amount of space we'll be taking is at most. Our function call is going to be at most height length, because by the time that reaches the end of, let's say, 5 or 1 here, that's when the stacks gets popped, or when the function calls are popped off, and then we have a new memory for the other side. So it'll be at most height long, and that's our space complexity. So our space complexity will be O of h, which represents height, which could also be n if our tree is just a single strand of nodes. So if it was just 3, 4, 5, the height would be equal to n. And as I mentioned, the time complexity is O of n, because we are revisiting every node exactly once, which there are n nodes, so it's O n. Thanks for watching.